We're surrounded by this invisible world of materials that literally powers our entire civilization. So today, we're going to dive deep into one of the most important and maybe most misunderstood of them all, the semiconductor. And I'm not exaggerating, seriously. That phone in your pocket, the computer you're watching this on, even your car, none of it would exist without these little unassuming chips. They are the absolute foundation of our entire digital age. But this brings up a really interesting question, right? The name itself, semiconductor. It sounds like a bit of a compromise, doesn't it? If we want electricity to flow, why on earth wouldn't we just use the best thing for the job, like copper? Copper's a fantastic conductor, so why would we settle for something that's only semi-good? To figure that out, we have to understand what makes a semiconductor so special. And spoiler alert, it has nothing to do with being the best at conducting electricity. It's about something way more powerful. Yep, the real magic, the secret sauce that kicked off a technological revolution, it all comes down to that one single word, control. Think about it like this. A conductor, like a copper wire, is kind of like a light switch that's just stuck in the on position. It's great at letting the juice flow, but you can't really stop it. A semiconductor, on the other hand, well, it is the switch. We can crank its conductivity up and down by a factor of thousands, turning that flow of electricity on and off whenever we want. So, how is that even possible? How do we get that kind of control? Well, to get the answer, we have to zoom in, way, way in, down to the level of atoms and the kind of weird quantum rules that they play by. Okay, so in a single atom, all by its lonesome, its electrons can't just hang out wherever they want. They're locked into these really specific energy levels. You can picture them like planets orbiting a sun. They can be in this orbit or that orbit, but they can't be anywhere in between. But here's where it gets cool. Atoms rarely are alone. When you bring two of them close together, those neat, sharp energy levels, they start to interact and they actually split. Now imagine scaling that up to a solid crystal with billions and billions of atoms all packed together. Those levels split so many times they just blur together into these wide, continuous highways of energy that we call energy bands. Now you've got all these energy bands, but for our purposes, we only really need to worry about two of them. You've got the valence band, that's where the homebody electrons live, they're stuck with their atoms. But for an electron to actually move around and carry a current, it needs to get enough of an energy boost to jump up to the freeway, and that's the conduction band. And this whole idea, the space between these bands, it's the secret decoder ring for everything. It's how we can classify pretty much any material into one of three electrical personalities. And that space, the gap between the valence floor and the conduction floor, it has a name. It's called the forbidden energy gap. Just think of it like a staircase. It's the amount of energy an electron has to gain to climb from its home in the valence band up to the conduction band. And just like a staircase, you can't just float in the middle of it. And this table right here just lays it all out perfectly. For conductors, like metals, those two bands actually overlap. There's no gap at all. Electrons can just wander over to the conduction band whenever they want. That's why they're always on. Now for insulators, the energy gap is massive. The climb is just impossible for an electron, so they're always off. But then, right in that sweet spot in the middle, you have semiconductors. They have a small, manageable gap. The jump is possible, but only if we give the electrons a little push. And that is what makes them a controllable switch. So that small gap, it's not a bug, it's not a flaw. It's the entire point. It's what gives semiconductors their almost magical ability to be controlled. I mean, this really is the key insight. The small energy gap isn't a bug. It's the entire feature. Having the ability to precisely control the current is so much more powerful than just letting it run wild all the time. For instance, if you could cool a semiconductor all the way down to absolute zero, as cold as it gets, there's just no energy in the system. Every single electron is stuck down in the valence band. It acts just like a perfect insulator. The switch is completely, totally off. But, and here's the cool part, just by letting it warm up to room temperature, the natural heat in the air gives a few electrons just enough of a kick to make that little jump into the conduction band, and boom, the switch is now slightly on and a tiny bit of current can flow. And this brings us to the final piece of the puzzle. How do we go from that tiny trickle of current to the super precise, lightning-fast switching that powers our entire digital world? We know the jump is possible. So what are the tools we actually use to give those electrons that push, to get them to jump exactly when we want them to? Well, it turns out we have a few clever tricks up our sleeve. We can add more heat, for sure. We can also shine light on it. Photons can hit electrons and give them the energy they need to jump. But the most powerful method, the real game changer, is something called doping. This is where we intentionally mix in tiny, incredibly precise amounts of other elements. These impurities basically create little stepping stones in the energy gap, making it way easier for current to flow. And by controlling this doping process, we can build all the fundamental components we need. We can make diodes, which are like one-way streets for electricity, and most importantly, we can make transistors, the microscopic, high-speed switches that are the building blocks of literally all modern electronics. And that's the bottom line. It's this incredible ability to flip a switch, to control the flow of electrons trillions of times a second inside a tiny piece of silicon that makes everything from a pocket calculator to advanced artificial intelligence possible. So we took a material that was just okay at conducting electricity, and we figured out that its real superpower wasn't conducting, but being controlled. By mastering that tiny little energy gap, we built the information age. It really makes you wonder, doesn't it? What other so-called imperfections in nature are out there just waiting for us to discover their true purpose?